All right, so we're going to get started here with the quantum session. So for the first talk is Andrew Litteken, who recently defended his PhD at the University of Chicago, where he was advised by Fred Chong, and he'll be working at Intel on their quantum compiler starting very soon. And he's going to tell us about Qompress. It's a work that explores using higher energy states to perform physical compression of quantum data to maximize the usefulness of a device while also improving circuit fidelity. So with that, take it away, Andrew.
Thanks. So like you said, I'm Andrew, and Qompress's work exploring a general way to make use of higher energy states for any qubit circuit to increase available computational space of a quantum computer by up to 2 times, while also improving gate fidelity. So in quantum computing, we usually care about qubits, which are devices that have access to 2 energy levels representing the 0 and the 1 state, and the ability to exist between the 0 and the 1 state, and entangling qubits with other qubits is what gives quantum computing the potential to be a transformative technology. But quantum devices can often access higher energy levels, potentially any number. When we access the 2 state, it's called a Q, or the 3rd state, it's called a Qtrit. When we access the 4th state, we call it a Qquart. And then, however, the use of higher energy levels leads to higher rates of decoherence or device collapse, as well as more difficult control, making this space a less explored area. But when we have access to the 4th level of a qubit, it becomes possible to combine the data of 2 2-level qubits into a single 4-level Qquart device through a compression or encoding gate. This compresses the information of what used to be 2 physical devices into a single physical device. So this has the potential to increase available computational space of a given architecture by up to 2 times. Like other quantum operations, the space compression is reversible, so we don't lose any data. By following the encoding shown, we can also develop a decoding gate that could separate these qubits, or just on measurement, we could recover the values of both qubits by looking at the value of the Qquart itself that we measure. So now we have a system that has 2 logical qubits encoded in a single physical Qquart. Well, we could use traditional Qquart gates to interact these qubits against with each other using the general Qquart operators of +1. To move the level of the Qquart up and down conditionally, we don't have to do that. It would be a kind of a cumbersome process. Instead, we design our own gate set using quantum optical control based on a realistic Hamiltonian for a superconducting system, based on the idea that whenever we have a Qquart, it is always 2 qubits encoded with one another. In particular, we define C0-based operations, which changes the value of a target qubit conditionally on the value of a control qubit, and swap operations or communication interactions between each possible pair of unencoded and encoded qubits, most of which are shown here, except for the basic qubit-qubit interaction. So we synthesize these gates to 99% fidelity for gates that involve 2 physical devices, and 99.9% when we involve 1 physical device. So this allows us to perform qubit operations on Qquarts and higher radix environments generally. We could apply this to any circuit. So a couple of things to notice here is that when we do this compression, it affords us much higher connectivity, potentially reducing communication costs when we actually map this to an architecture, since on most architectures, qubits do not have all-to-all connectivity, so we have to insert communication gates. And it also provides us with an internal C0 gate that interacts 2 qubits with one another that are encoded in the same Qquart, and that has 10x higher fidelity and is 5 times faster than the equivalent gate on 2 unencoded qubits with 1. So these are great motivators for trying to use qubit on Qquart computation generally. So further, we find that Qquart-based computation may not be as expensive as previously feared. So the scaling was thought to be quadratic, and in this image, we show the hierarchy for gate durations in our new system on the left, and time for selected gates on the right. Beyond the 5 times faster internal C0 gates as compared to the standard qubit-only C0 gate, we see that the partial swap operations, so that's operations between that involve only part of the Qquart, and only involve 1 qubit inside of an encoded Qquart. are not as expensive as we previously thought. Like we can compare it to the full swap, which swaps the data between two Qquarts entirely, and we find that by using the smaller computational space of the partial operation, it's much cheaper than just doing full Qquart operations. But even with the expanded connectivity, we cannot simply run a quantum program on any architecture. So we developed compiler algorithms to transparently make use of qubit on Qquart operations without input from the original programmer to efficiently balance the trade-offs of higher Q to interactions with the benefit of higher fidelity gates, while also balancing and higher connectivity with the slower overall Qquart base gates. So we expand mapping and routing algorithms for qubit only computation by developing an expanded physical interaction graph. So we consider each physical device to contain 2 qubits with connections as we show here. And then when we need to find a communication path to interact 2 qubits with one another, we dynamically estimate the cost of the swap path based on the estimated incurred error, which are based on the fidelity of the gates used, and also the possibility of decoherence error as the operation occurs as well. So as the operation is longer, there's a higher chance for decoherence. We might want to avoid using longer paths or gates with longer durations. So we maintain an accurate mapping of the current qubits in a given Qquart that are filled at any given time, so we can accurately determine the cost of a given swap path, since each operation costs change based on whether a device is maximally in the qubit state or the Qquart state. So more pressing is the fact that finding an advantageous set of compressions to start with that actually improve circuit fidelity is somewhat difficult. So this graph shows a greedy strategy that looks at all the possible pairs of circuit and then remaps and reroutes the circuit at each step, and we pick the best option with some constraints. And this continues until all the qubits have been compressed into a full Qquart system. So what I really want to point out here is that not every compression is advantageous. Some can actually hurt the fidelity of the circuit overall, and some of these are driven by compressing interactions to use that higher fidelity internal Qquart operation, and some are improve the gate fidelity by reducing communication distance overall. So we designed several different strategies this work. Only a portion of the ones that are mentioned in the paper are shown here. The first is that greedy strategy, which is exponential in cost. And we look at this as our goals, because we have all the resources. We don't care about how long the mapping routing is going to take us. And then we also want to improve upon a second previous baseline strategy, which only uses those full Qquart operations and has to decode the qubits in order to perform cross-qubit operations. And the last one is extended qubit mapping, which uses that adapted distance function based on error to try and perform clustering such that we can advantageously map the circuit onto the architecture without any swaps at all. So in here, we can we can find compressions that make it so that we just have to map a line, which is usually pretty easy on most quantum architectures. So we compare these strategies on a bunch of different benchmarks that scale to any number of qubits. So these graphs represent an estimate of represent the factor of improvement in terms of gate error. So the y-axis is the product of gate errors for a Qquart-based compilation over the expected probability of success, that gate product, versus for a qubit-only system. It's just the ratios, it's the factor of improvement. And then the x-axis is just the size of the circuit. And the black line that we show here is the goal strategies. It was the greedy strategies, the one we want to be able to either match or exceed if possible. So we're going to look at the top 4 circuits first. These are more arithmetic circuits. They include a lot of 3-qubit gates. And we find that our extended qubit mapping strategy is mostly able to match the greedy exponential solution that we explored before, when we have all the resources all the time in the world. In the case of this arithmetic circuit, because we're able to easily find the compression that will reduce the circuit into a single line, which allows us to map and route the circuit without any swap gates due to that higher connectivity that we'd explored before. And also, because we can perform this compression, we have access, we use many more of the internal CNOT gates inside of the Ququart as well. The extended Ququart mapping is able to discover these structural relationships pretty easily. For the other 4 circuits, they are based on specific graph structures with 1 2-qubit operation for each edge in the graph. So these are to try to explore, are there certain shapes that work well for this compiler. So each of these, so the QAway is just a random graph. The cylinder is just a grid where it wraps around itself, so left and right are connected. The torus is connected at the top and bottom as well, and then the binary welded tree is just 2 binary trees connected at the leaves. So we aren't able to easily find those sorts of really good compressions that we were able to find for the arithmetic-based circuits. But we're still able to find compressions that are decent enough, and we're able to match the gold strategy where we did that exponential exploration. This indicates that the strategy is generally viable, even in cases where there's not that very particular relationship between the qubits. However, I mentioned that higher energy states have an extra cost. They decohere much faster than just the regular qubit circuit. So in this case, these graphs have the ratio of the error due to decoherence for a Ququart state over the error due to decoherence for a qubit only compilation. And so while we're never actually to exceed the circuit, we're never able to improve upon the decoherence error for the qubit only circuit, we're able to be mitigated as well as the greedy solution which we found before. This is mostly because when we have Ququarts, we do somewhat serialize the circuit a little bit because we can't interact with both qubits in the Ququart at the same time with with qubits outside of that Ququart. So this alongside the reduced T1 time, the reduced coherence times result in this drawback. But in general, these errors currently just sort of cancel each other out. So using the Ququart based strategy is not worse than the qubit only strategy. So overall, this work shows a strategy to compress quantum information from qubits into Ququarts, maintaining similar fidelities for any qubit circuit, increasing space on quantum devices by up to 2 times. This is enabled by developing a new set of Ququart gates and partial Ququart operators via quantum optimal control, which we are then able to give to a compiler which achieves the circuit fidelities by taking advantage of those higher fidelity internal qubit operations, higher connectivity, and faster than expected partial Ququart operations. So thank you for your time. Are there any questions?